Please remember we have an exam on Friday. Okay, so come with your sheet of notes. Today we're going to take a look at the Bode phase characteristics. I'm going to first go over the characteristics of each of the different types of factors that we look at. And then if time permits, we'll do an example again. Maybe we'll look at the phase characteristic of the system that we sketched the magnitude characteristic for on Monday. So again, let's take a look at the basic factors. You may have the first factor is a gain, just a number, a gain k like this. And we're looking at the phase characteristic of this number. So think about this number is think of it as being k with an angle theta. Okay, if it's just a number like 2 or 3 or 4, something like that, then theta has either one of two choices. Theta is equal to 0 degrees, or theta is equal to 180 degrees. Okay, so -3 would be 3 at an angle of 180 degrees, and so this would be the phase. A +3 would be a phase of 0 degrees. Now there's some ambiguity. It's ambiguous because you got to decide whether it's 180 degrees or minus 180 degrees. Okay. If I told you, I said turn 180 degrees, you would go like this. Okay. If I said turn negative 180 degrees, you would go like this. And in both cases, you would end up in the same place. Now, on a Bode diagram, this is ambiguous because 180 degrees, if this is 0 degrees right here, you would plot 180 degrees up here. It's on the top of your paper. But negative 180 degrees is down here on the bottom. And so it looks like they're two different places, but they're really pointing in the same direction. So there's a little bit of ambiguousness now. You'll see this in the hardware. This causes a problem sometimes in spectrum analyzers. In a spectrum analyzer, what will happen sometimes is maybe say this is 180 degrees down here, negative 180 degrees, and we start off 0 right here. So sometimes what they'll do is they'll plot, and maybe the phase is going down here, and it hits a negative 180 degrees. So they say, well, I can't plot any further. And I know that I've run out of paper down here, or I've run out of screen down here. But I do know that positive 180 degrees and negative 180 degrees are the same. So what you'll see is the plot coming down. It'll hit 180 degrees, and then all of a sudden the plot will jump vertically 360 degrees up to the top to plus 180, and then they'll continue plotting. Now you'll look at that characteristic, you see this jump, and you say, what's going on? It's because positive 180 degrees up there and negative 180 degrees down here are really the same thing. So this is called wrapping. They're called wrapping the plot around. And if you don't like that jump, sometimes they have a button that says you can unwrap the plot. But you need to realize there's some ambiguousness on the Bode plot sometimes when you see this in a real plot that's produced. Okay, so that's one of the basic factors, is just the gain. 0 degrees or minus 180 degrees is all we have to deal with. The second type of factor is a term that looks like S, all by itself. So remember, S in the frequency response is we're just looking at j omega. So this is just a purely imaginary number. And if we take a look at the phase of a purely imaginary complex number, that's just plus 90 degrees. That's the phase of that factor. It doesn't change with frequency because no matter what the frequency is, this is purely imaginary. In a similar fashion, 1 over S in the frequency response is 1 over j omega. 1 over j, again, is purely imaginary, and the phase is always negative 90 degrees. Okay. You may remember when you're looking at the characteristic of an inductor in circuits, you looked at SL. That was the impedance. The voltage leads the current by 90 degrees, plus 90 degrees. you have 1 over SC. The voltage lags the current by 90 degrees in a capacitor. So this is from circuit analysis. You may remember this for sinusoidal currents, there's this 90 degrees, plus 90 degrees and minus 90 degree characteristic for inductors and capacitors. So that might help you remember the phase for this. The third characteristic that is simple is the first order term. So let's take a look at a term like S plus A. Okay, this is a 0. On the frequency response plot, let's put the, this is the frequency axis here. There's a corner frequency A. We need to identify A for the magnitude characteristic. But for the frequency response phase characteristic, for the phase characteristic, there are 2 different corners. We put one corner at a decade below A and another corner a decade above A. So here's the corner frequency. This is the corner frequency in the magnitude. But in the phase, there are 2 corners. So this is why I said a few days ago, I said if we know how to do the mechanics of sketching the magnitude plot, then we'll know how to also do the mechanics of the phase plot, because it's just a matter of changing the slopes at the corners. The complication is that there are twice as many corners. On the vertical axis, this is going to be phase. I'm going to just say this is phase in degrees, like this. This is the angle in degrees. The phase will do this. At this corner, everything comes in flat at 0 degrees until it hits the corner. And then it starts lagging. Leading. This is a 0. It'll start leading, so it starts doing this. It starts going up, and then it hits the second corner, and then it flattens out again. And so this will be up at plus 90 degrees. So the phase changes from 0 to plus 90 across 2 decades. You think of this as 45 degrees per decade. The actual phase is going to have a little bit of error here at the corner. And it'll go through here. It'll be correct right here in the middle. And then it'll be a little high. And then it's a smooth curve like this. But we draw straight lines with corners here and here. Let me squeeze on in here the same plot, 1 over S plus A. This is a pole. Maybe I should call this 3B. This is 3A and this is 3B. The pole is going to be just the opposite of a 0. It's going to have the same corners at 0.1A and 10A, but the phase I'm going to sketch in with a dotted line will do this, and it will end up at minus 90 degrees. That's the pole. The actual curve will be something like this. The other factor that we have to deal with is the complex term. Let me put that on another page. Slide this up here. We'll put the complex term. Let's call that 4. The complex factor, we can draw, again, the scale. Let's say we have a complex factor that looks like, let me do zeros, s squared plus 2 zeta omega n s plus omega n squared. We have a factor that looks like this, complex zeros. The corner in the magnitude plot is at omega n. In the magnitude plot, the corner is at omega n. We want to know that for Friday. The corners in the phase plot are, again, a decade below, 1 decade below omega n, and 1 decade above omega n. The phase is going to start at 0 degrees. And because it's a 0, it's going to start increasing, complex zeros, complex conjugate pairs, and it will increase like so until it hits this corner. and it will reach positive 180 degrees in 2 decades. So this slope is 90 degrees per decade. If we have a complex conjugate pair of poles, so that the factor looks like 1 over s squared plus this, then the characteristic looks just the opposite, and things go down to negative 180 degrees. And the slope is negative 90 degrees per decade. Now, these are the straight line approximations. The actual curves will be a family of curves that depend on zeta. Zeta controls a family of curves. If zeta is close to 1, then the curve is kind of gradual. I'll sketch it in like this. It looks kind of like this. Kind of do a smooth curve that looks like that. But if zeta is small, then the curve becomes more squarish like this. And in the extreme, when zeta is equal to 0, it just looks like a step occurred right here. And so that's one of the ways that you can identify the corner frequency. If the system is lightly damped, you'll see the phase suddenly change like this from 0 to 180 degrees. Now, this is not what I was talking about earlier when I was talking about wrapping, how a spectrum analyzer might plot down to 180 degrees and then suddenly jump 360 to plus 180. I'm talking about here how the phase characteristic may jump from 0 to 180 degrees when zeta is very, very small. So when zeta is small, we see the very sharp jump here in the phase characteristic. We see a peak in the magnitude characteristic. Let's review all of these plots. The gain plot is constant. It's either 0 degrees or 180 degrees. It's just a flat line. S and 1 over S, again, are flat lines. They're just either at plus 90 or minus 90. They're flat lines. They come in flat and they go out flat. Look at the first order term, and you see that it comes in flat and it goes out flat. It just changes 90 degrees, either positive 90 degrees or negative 90 degrees. And the complex factor also comes in flat and it goes out flat. So in some ways, the phase plots are a little bit easier than magnitude plots. We don't have to worry about getting the initial slope correct. The slope's always going to be flat if our window is wide enough. If my frequency window is too narrow, then maybe it looks like the slope is changing. But if I make my frequency axis wide enough, the phase will always start flat and end flat. So here's a few more notes that we need to make. Let's make a few more notes about the phase plot, some observations. Some observations. That's a V right there. Okay. The initial slope, initial and final slopes are always flat. Okay. Initial and final slopes are always flat in the phase plot. The other thing that I want to introduce is a term called the relative degree. The relative degree is equal to the number of poles minus the number of zeros. Okay. So for example, 1 over s plus 2 has a relative degree. Let me call this relative degree r. R is equal to 1. 1 over s plus 3 over s plus 2, r is equal to 0. Okay. Now there is something that we need to know about phase plots and the relative degree. The phase at high frequency is equal to r times negative 90 degrees. Okay. So here the relative degree is equal to 1. So the high frequency phase is negative 90 degrees. Okay. The relative degree here is equal to 0. So the phase at high frequency is equal to 0. Now this observation is true for the case where all our coefficients are, let me put it this way, we have no poles and zeros in the right half plane. Okay, no poles and zeros are in the right half plane. Let me make a comment about that. This is one complication of the phase plot that one needs to be aware of. In some ways, the phase plot is easier than the magnitude plot, but here's where there's a complication. So basically, this issue here, poles and zeros in the right half plane, you get the tip-off is negative signs. Okay, so what do I mean by poles and zeros in right half plane? What do I mean by that? Okay, let's take a look at 1 over s plus 2. In the complex plane, if this is the real axis and this is the imaginary axis, this is a pole here at minus 2. If I have 1 over s minus 2, this is a pole over here at plus 2. Okay. Everything that I'm going to, all the examples that I'm going to do today, all the examples that I'll do, anything that I'll put on exam will not include this case. Okay. All the phase characteristics that we're drawing are for this case. As soon as you get minus signs like this, you need to go back and ask for more money. Okay. You can go back to fundamentals and figure out what is the phase of a characteristic. Basically, the slope directions all change, and it can be complicated. Well, on another day, I'll bring in a worksheet, and we'll go through this just to reinforce the fact that the phase characteristic is much more complicated. You really need to go back and use MATLAB. As soon as you see a minus sign somewhere in here, you need to just arrest yourself and just say, wait, this is going to take a little bit more time because the phase is more complicated for a case like this. We are going to deal in this class, in all of our problems, all of our examples, all these signs are going to be positive. The only exception will be this case where the gain could be a positive or minus sign, because that's easy. That's just a 180-degree phase shift. But anything else, all these ideas about these slope changes, their directions all change. So over here, all our rules for quick sketches apply here on this side. Over here, rules are different. Slow down. Use MATLAB or something like that. Use some calculator to do the work. As soon as you see a minus sign, you need to arrest yourself and say, wait, this is something with a characteristic over here in the right half plane, and I need to arrest myself. Okay. What might be a characteristic? What causes things to be in the right half plane? Well, if it's a pole in the right half plane, it would be an unstable system. What about a zero in the right half plane? An example of something of a model that has a zero in the right half plane is a fishing pole. Okay. All right. A fishing pole is a long, flexible beam, and you know that if you cast this way, the pole is going to bend. So let's suppose I say that I want to point. My pole is initially upright, like this, and I want to point it that way. So what I do is I take my hand and I twist the pole like this, and it's supposed to go that way. But anybody who's done some fishing knows that the pole is going to bend right? It's going to do this. Let me see if I can imagine this is the pole. If I torque the pole and try to move it this way, it's initially going to flex like this. It's going to flex like this, right? It's pointing straight up and down. And when I torque the pole, it's going to bend like this. When it bends like this, what happens is momentarily, the tip of the pole is going to point that way. I push the pole this way to point that way, but momentarily the tip points that way. That's the opposite direction. Mathematically, in differential equations and things like that, it looks like a 0 in the right half plane. So it can cause problems in feedback systems. All right, so these are the observations. Initial slopes are always flat in the phase plot. We need to know the relative degree. This is just as a check, because we can determine that the phase at high frequency is always going to be r times negative 90 degrees. And all of our rules that we're going to look at today and for exams and stuff like that, we're going to look at rules where all the signs are positive. We don't have any poles or zeros in the right half plane. Otherwise, we need to slow down. So let's do an example. I'm going to try to recall the example we did on Monday. We did the magnitude plot. Let's sketch the phase characteristic. We desire the phase of G of S. G of S on Monday, I think the phase, the model, somebody might look at their notes, I think it's 240 on the top, and then there was a S, I believe there's S plus 5, S plus 0.3, S squared plus, I don't remember, 20S, something like that, and there was 900. All right. So we got several different types of factors, and we're going to put it all together. All right. Notice all the signs are positive. Okay. No negative signs floating around. Okay. If I see a negative sign here, or here, or here, or here, or here, I immediately say, hey, let me take you out to lunch. We'll sketch it out on the back of my napkin at Chick-fil-A. Oh no, Chick-fil-A's been torn down. Anyway, we'll have to take a long walk. It'll take a little bit. We'll have to talk about it more if there's a minus sign here. Now, if there's just a minus sign out here, that's no problem. We just simply shift things by 180 degrees. All right, so the things that we have to deal with here, we see no positive signs, okay, no negative signs, so there's nothing to deal with. But let's take a look at the different factors. We have a 0 at omega equal to 0. That's this term. And so that means that we have a initial phase is equal to plus 90 degrees. At low frequencies, all these other factors start at 0 degrees. This starts at 0 degrees and goes to negative 90 degrees. This starts at 0 degrees and goes to negative 180 degrees. This starts at 0 and goes to plus 90 degrees. So all the factors start at 0 except for this one. This one's always plus 90 degrees. So that's why I say the initial phase has to be equal to plus 90 degrees. When I say initial, I mean low frequency. At low omega, 90 degrees. Now we have a bunch of other corners to deal with. And this is what I like to do. I like to list the corners. Let me list, first of all, the magnitude corners. And then I'll list here the phase corners. And then I'm going to put here the phase changes, slope changes. This is the same technique that we use for the magnitude plot. We list all the corners, and we list all the changes, and then we just simply draw lines, changing the slope at the corners. But it's just that we've got twice as many corners. So let's see, I've got a corner here at 0.3 in the magnitude. 0.3 gives rise to 2 phase corners, a decade below, which is 0.03, and a decade above, which is 3. This is a pole. This is a pole, so the slope change here is negative 45 degrees per decade. Here, the change is going to be plus 45 degrees per decade. Let me bring back the picture of the first order pole. It's this one right here. First order pole. I hit the corner, and then the slope changes to negative 45 degrees per decade. And then here, it increases to plus 45 degrees per decade and becomes flat again. Yeah. So there are 2 changes we have to deal with. Another corner is 5. Omega equal to 5 in the magnitude plot. But in the phase plot, that means there's going to be 2 corners. One at 0.5 and one at 50. This is a 0. So at the first corner, the change is going to be plus 45 degrees per decade. And then at this corner, it flattens out again, so the change is negative 45 degrees per decade. We have one final factor. We have a magnitude corner at omega n equal to 30, square root 900. So that gives rise to 2 corners. One is at 3, and one is at 300. And so at 3, because this is a pole, okay, this one was a pole. This is a 0. This is a complex second order pole. So the first change is going to be negative 90 degrees per decade, and then the next change is plus 90 degrees per decade. Okay. Now, notice that I've ordered the corners in the magnitude. I've ordered the corner frequencies from lowest to highest in the magnitude sense. Okay, 0.3, 5, 30. But notice that the corners here, you know, this corner here is in between these two. So it makes our life a little bit complicated. We need to, when we put our breadcrumbs, we need to make sure we keep track of what all the different corners are. So let's pull out our Buddy plot paper, our semi-log chart. This is a semi-log chart, logarithmic, only on one axis, semi-log. Let's orient it correctly. Let's orient it this way. The frequency is compressed at higher frequencies, expanded at lower frequencies. We need to label this axis. We're going to call it frequency. Let's say in school it's radians per second. On a machine it would be hertz or something like that. We need to have a frequency axis that covers this range, as small as 0.03 and as big as 300. So let's stare at our frequency axis and see where we would put things. Let's see, if I put 100 here, that would be 10. That would be 1, 0.1. I may be in trouble here, guys. If this is 0.01, 0.01, 0.1, 1, 10, 100. I'm a little bit of trouble, but I can't fit everything on. 0.01, 0.1, 1, 10, 100. I can't get 300 on here. I'm in trouble. Okay, this is a 4-cycle log paper. I need 5 cycles, but we'll try to get that idea in anyway. Let's label this as phase in degrees. Okay. the initial slope is 90 degrees, so I need to make sure 90 degrees is on here. So let's do this. Let's call this, let's see, the relative degree here is, I got 3 poles, 1, 2, 3, 2 zeros. Relative degree is equal to 1. So let me make a little note right here. Relative degree R is equal to 1. I have 3 poles, 1, 2, 3, 2 zeros, 1, 2, so the relative degree is equal to 1. So it should be at negative 90 degrees at high omega. Okay. So at low frequencies, I need to be at plus 90 degrees. At high frequency, I need to be at negative 90 degrees. So I need to make sure plus 90 and minus 90 are on my plot. So let me put 0 right here. I'll call this 45, call this 90, minus 45, minus 90. Okay. So at low frequencies, I need to be coming in here, and at high frequencies, I better end up over here. So I'm going to draw a straight line. I'm going to change the slopes just like I did with the magnitude plot. Every time I reach a breadcrumb, a corner frequency, I'm going to go up, down, and stuff like that. But I better end up here. If I didn't end up here, then I just made a drawing error. Okay. So let's mark our corners. We got 0.03. Let's say 0.01, 02, 03 is right here. 3 is here. 0.5. Let's see, 0.03, 3, 5, 0.5, 0.1, 0.2, 0.3, 0.4, 0.5, 50, 10, 20, 30, 40, 50, 3, ooh, I got a corner here. This is really a complicated example. Well, that's good. We got 2 corners to deal with. And then 300. 300 is off the page, but I'm going to estimate it is roughly about here. Okay, so out at 300, it should be flat. Okay, these are all our breadcrumbs. So let's put. It might be helpful to just have this table right next to us so that we know what's going on. Okay, so I come in flat. And until I reach the first corner, which is 0.03. So I come in flat until I reach 0.03. And 0.03, the slope change is negative 45 degrees per decade. So I need to change the slope to 45 degrees per decade. And that will look something like this. Okay. So use the same technique that we did before with the magnitude characteristic. Just extend the line toward the right. Each time we hit a corner, we change the slope. And we look at our table and say, oh, the slope is negative 45 degree change. So it was flat, the change is negative 45 degrees, so that means the new slope is flat like that. Okay. And I do that until I hit the next corner. The next corner is 0.5, so I got to find 0.5 in my table and see 0.5 is, oh, a plus 45 degree change. So that means the new slope is going to be flat like this. Let me ask if I'm going too fast. Just a table of breadcrumbs over here. My corners are here. They're listed here. I'm just pushing the line to the right. Each time I hit a corner, I adjust the slope up or down depending on what the characteristics are. These rules are great for when all the signs are positive, but if there's a negative sign, all bets are off. Okay, now we get here, 3. And apparently I've got 2 changes. So I need to combine them. Negative 90 and plus 45 is negative 45. So the net change is negative 45. So I need to do something back down like this again. So this slope here is, right here, the change was negative 45 degrees per decade change. And here the change was plus 45 degrees per decade. Here the net change was negative 45 degrees per decade. These are the changes. The actual slopes are a different number. Okay, you may notice on some of the exams I'll ask you to label the slopes. The slope here is negative 45. The slope here is 0. The slope here is negative 45. What I've labeled here this morning is the change at the corner. It's not the slope. It's the change in slope. Okay, so I've taken care of this, this corner, these two corners. I got to do 50. At 50, the slope change is negative 45 degrees per decade. So it's negative 45 degrees per decade. So I got another slope change here at 50, which is about 30, 40, 50, right about here. And so it should be steeper. The net's, this is another negative 45 degrees per decade. The net slope is 90 degrees per decade. It's more steep. And it's going to be something like this. It's more steep. Okay. And then I hit the last corner, and look at what happens here. The last corner is 300, and the slope change is plus 90. This was going down at minus 90 degrees per decade. I got a slope change at plus 90, which means the net slope is flat. And so I've done everything right. It comes out flat. And if I draw my lines accurately, it'll come out right here at negative 90 degrees. If I didn't draw my lines accurately, it comes out at some number that's not some multiple of 90 degrees. This is the straight line approximation. The actual curves are going to have some errors around the corners. Except in this case, we have a complex term, omega n 30. The damping is small. So around 30, which is 30 is right here, right here, the slope is going to change drastically. So don't expect a nice gentle curve in this area. It'll probably do something like this. A lot of error right around here at omega n equal to 30 is right here. Right here in this vicinity, the actual curve will do something drastic like this. But the straight line approximation is what we sketched in. Okay, so this problem had several complications were probably good that we pointed out. Number one, we ran out of space. Number two, there were some corners on top of each other, so you got to take the net. Okay, very quickly, what would happen if I were to come in and say, now that you've got this plotted, let's put a minus sign here. If I have a minus sign here, what will we do? Okay, you can shift it. Just shift the plot. You can shift it up 180 degrees, or you can shift it down to 180 degrees. 180 degree shift is what you need. Any other sign changes would be more complicated. All right, so we will pick up with phase plots again on next Monday. We'll do some more examples. We'll look also at this complication of negative signs, just to reinforce the idea that negative signs deserve more money. But for Friday, we're going to have an examination on up through Bode magnitude plots. All right, any questions, comments, discussions? Okay, y'all have a good